All right. While we set up, jump up, stretch, move your hands a bit. So I'll already start talking to get everything, myself and you included, warmed up. So I'm Aapo Alasuutari. I work as a TypeScript JavaScript programmer. I don't write Rust or I don't make money with Rust. I don't turn Rust into money. I barely write Rust. I'm pants at it. I'm very bad at it. I'm not going to show any of my code, and it's not because I don't want you to see it. It's horribly uncomfortable to show it to people. Like, look at this. It's great. No, it's not. But it's loading. Yeah. So earlier we mentioned that, or Henry mentioned that we were going back to the kind of traditionals of Tampere Rust meetups, which was embedded devices. So here's the other. Now I'm already making myself a tradition. So this is now a JavaScript conference. So we're going to be talking about building a JavaScript engine. This particular engine is called Nova, and it's a DoD, so data-oriented design-based JavaScript engine. So what on earth is Nova? It all starts with a joke. So a bunch of Dino enthusiasts walk into a Discord channel one night, and we're going to skip right to the punchline. So when are we starting our own JS engine? Now I need to pronounce this correctly. Andrew, no, that was wrong. Anyway, Andrew asked, and we started our own JS engine then. So this was nearly, what? Yeah, nearly 2 years ago or something. What? It's been a long time now. So we made some initial commits, started like a WASM engine. We bike shed the name, decided on, supernovas, so on and so forth. Space is very cool. Started working on the JavaScript engine structure, started our own parser, made a PR to start actually working with JavaScript values. It was based on the GC crate. If anyone has seen this particular Rust crate. So this was always written in Rust. I didn't actually mention it here, but yeah. GC crate provides reference counted GCable heap allocations, basically. And with an it's not reference counted, but traced. And it has an automatic derived GC implementation, so you can kind of very easily set up stuff with it. And we also had a dynamic object trait. And then we removed the parser, started using OXC, the oxidation compiler, which is lovely. And then we just mostly did nothing until last summer. I then heard of data-oriented design or entity component systems from a friend of mine who works in gaming, in the gaming industry here in Tampere. And that piqued my interest. I started thinking, now that would be very interesting for a JavaScript engine. Now that is something. So Nova Engine today is a stack-based bytecode VM. So we use the oxidation compilers AST crate and parser crate to parse JavaScript code into an AST, abstract syntax tree. But then from that syntax tree, we immediately generate bytecode. We don't use the AST aside from that. And the heap design for the virtual machine is built in a data-oriented way. What that means, I'll talk about that in a bit. In horrible length. And the project structure is built around the ECMAScript specification itself. How many here have read language specifications? It's fun stuff. I've only read the ECMAScript specification. It's actually rather nicely structured. Like, you can kind of read through it and see, yes, okay, that's how this works, and that's how this works. And why are you talking about that thing now here? It's why? Okay, whatever. It's probably the same for other languages as well. But the idea is that generally, if there's a section in the specification, we'll have a folder for that. If there's a subsection, then either we have a module or a subfolder for that, depending kind of on how deep the rabbit hole goes. And then when the spec starts to actually explain abstract operations, we'll have a function for that in the module. And the intention here is, of course, that this should be easy to understand for someone who has ever read the ECMAScript specification. It should be really easy to actually read one part of the specification and just start bashing out the abstract operation into Rust. And then, like, if the spec changes, if there are any updates or so on, we can just kind of take a jump from our implementation. There's already like a direct link to the specification. We can open that, see how it has changed, start fixing the issues. So, okay, that's what Nova Engine is, but what on earth is JavaScript? I mean, ECMAScript. So JavaScript is owned by Oracle, and it's just a name, trademark. So we talk of ECMAScript. ECMAScript is a dynamically typed language. In general, it then means that there is no information about what type a value is. Not when you're writing it, not when you're parsing it, not when you're compiling it, because you're compiling it. It's all only at runtime. And the type system itself is also, of course, needs to be fairly limited to accept this kind of unknownness. So there's undefined, there's null, two different bottom values. That's a great idea. Like, of course, how about we have like none, and then we could have like maybe. Would be fun. Strings, booleans, numbers, big ints if number is not enough for you, and symbol for magical things, and then object. That's it. Anyone spot anything missing? No floats and no functions. Yeah. So floats go into numbers. So the number in JavaScript is a double, except that it actually works differently with bitwise operations. When you do bitwise operations, it's a 32-bit signed integer. There's actually, I only realized or saw this like 2 days ago. ARM architecture, the processor has a specific instruction for calculating the JavaScript or the ECMAScript specs double to 32-bit signed integer operation. Okay. But yeah, so there are no objects because functions are objects. Aha! You didn't see that coming. No, yeah. So functions are objects. Arrays are objects. Array buffers. So that's like your normal vector. You would think like vector of U8s. That's an object. Everything is object basically. If it's not primitive, it's an object. So the ECMAScript spec then mostly deals and mostly talks of these values. And because the spec mostly talks about values, the engine mostly talks about values. There are some abstract operations which take as parameters, let's say, a string or a number or something. But those are specific cases where you know from the parsed code what is happening. But then when it's an actual like built-in function or something, it just takes values because it can be called with anything. Okay, so I'm going to quote quickly Chandler Carruth from 2014's CPPCon. Efficiency comes from operations or functions, and performance comes from data structures. So how does an engine actually implement a value is one of the most important questions that the engine needs to answer to then figure out how it's going to be performant. One option how to do value is do just like copyable value on the stack. So you would have some kind of massive thing that just can hold any type of value. It can hold any type of object and all the data associated with it, at least those parts that can be on the stack and like are not kind of must on the heap. And yeah, so the doing this, you would end up with a huge object or huge value because it always needs to be as big as the biggest value is. And you would need to have some internal discriminant in this data that knows, like, okay, what type of value is this? Another choice is to have a reference to your value be a reference to the heap. So your value is just a pointer. And then the heap is where your data is. Now your pointer, it can be typed, so its size doesn't change, and well, you still need an internal discriminant there on the heap. You can do some mitigations here, though, to maybe get rid of some of those. But that's another option. Kind of a rustier option would be to do an enum. So we do an enum with the payload being some kind of a reference to data on the heap. Or possibly it can be, of course, just stack data as well. And now, if we do this, we might not require an internal discriminant in the data itself, because we already have the enum discriminant. We could maybe kind of use that. Let's see. But there's one question, of course, is your payload, is your reference going to be a pointer? Or is it going to be something else? So how would a heap reference value work? This is how V8 does it. This is how JavaScript core also does it, basically. So the very naive implementation is to take a reference, and it's just a pointer, and the heap allocated value has that discriminant. V8 does something a little bit different. They do a tagged pointer. So their pointer contains a tag which tells, is the pointer actually a pointer, or is it actually an signed integer on the stack? And this is fairly simple, works well enough. It's well proven to be performant enough. It handles the most important special case, the I32, on the stack. And unfortunately, this means that only the heap knows what type of data you're dealing with. So when you see a value, you can check the tag to see if it's a small integer. But if it's not a small integer, then the next question you're going to ask is, what kind of data is this? That's a heap read. JavaScript core kind of does the same kind of thing, but they use a nan-boxed value. So this is Safari browser. So either their value is a valid double, F64, or it's not a number, in which case the 3 upper bits of the mantissa after the signaling bit contains a tag which then tells, are the bottom 48 bits going to be a pointer, or is it going to be some stack value like an I32 or something? This means that you can have full doubles on the stack. That's great. All JavaScript numbers basically are now on the stack. You can also probably put a lot more stuff into the 48 bottom bits that you get as payload. And you can discriminate the data a bit more on the stack with the nan tag. So you could have different kinds of pointers. Not just that, yeah, this is a pointer to the heap, but this is a pointer to a string. This is a pointer to an object, a pointer to a symbol, so on and so forth. You get 3 bits, so you can get 8 different values. But the downside here in both of these is that you're messing with pointers, mate. That's not good. Are you crazy? No. Unsafe and iffy. If you do any of this in Rust, you need to use the unsafe keyword. And we don't like that, not here. Okay, we actually kind of do, but let's just pretend. Also the nan boxing, which kind of, if you look at it far enough, it seems to be the better one here. It's obviously getting more stuff onto the stack out of the heap. This breaks with 5-level paging. Intel is kind of pushing for that, I think, or at least makes it possible. And ARM is doing pointer cryptography, starting from 8.3 or something. And that, either of those completely breaks nan boxing. You cannot do nan boxing anymore with that because of how pointer upper bits are then used. All right. So this is a bad idea. Let's not do that. So let's go with the Rusty solution. Let's use an enum. So we take a Rust enum with a payload, and let's first ask ourselves, what is going to be the representation of our enum? Like, okay, we could just let Rust decide, but it's going to probably decide a U size for it. And that's a bit too much. We really don't need 2 to the power of 64 different variants. So no, thank you. The ECMAScript spec talks about 50 different types. And now I'm saying here type not as in JavaScript different value types, but just different kinds of objects plus all the primitives that you can find in the spec mentioned. So 255 should be enough. So we'll just use 1 byte as our enum discriminant. So then what about the payload? The obvious choice would be to use the pointer, but then our value is now 16 bytes. And 7 of those bytes are just filler, because you've got the discriminant, and you've got to get a pointer there. It's just empty there. That's horrible. No. We know the type of our value based on the enum variant. So can we then place the data for that type, T, into some arena that we can know, and then in a way kind of compress our pointers small enough that we could fit it in, or to end up with our value compressing down to 8 bytes. What kind of memory arena could we do? Well, a VEC. Yeah, sounds good enough. So VEC, that's a memory arena of type T, right? And one good thing, first of all, here is already that when you index into a VEC, the type or the index you give is a U size, yes, but it's not a memory offset into the vector. It's the index into the vector. That already compresses your pointers. Instead of you saying that, please take byte offset 2555 or something, you say, please give me index to 12 or whatever, and Rust will compute that automatically into a memory offset inside the machine, or the computer does it for you. So we don't need to store a memory offset. That compresses our pointer. That's nice, but also it's actually possible to just say, like, nobody's ever going to need more than 2 million items of any type T. So we don't need a U size. We can use a U32. So we use a U32 as our index into a vector of T, where the T is based on the representation or the enum variant. And our value just becomes a U8 and a U32. Stack knows the type of an item. It knows the index into a heap vector for that type. The way you access this particular data for this item is then to ask the virtual machine, you get a pointer to that thing, please give me data, or more like, please do some abstract operation on this value. Here's the type and its index. So it does it. Yeah, lovely. But can we do more? Is that it? No, we can do more. So we have about 200 discriminants left. That's plenty enough to do some fun things. So let's make a custom discriminant for I32. That's the most important stack case, kind of. What other things can we do? We still have 3 bytes that we were not using, so we can actually do U8 with 7 bytes of data, and this still fits in our value. So we can do actually an I56. Rust doesn't give us 56-bit integers directly. There is a proposal or RFC for this kind of magic, but I'm not sure if it would work here. But we can just do this manually. We just new type a 7-byte array. We can also do 7-byte short string optimization. So length, data, value, these sorts of strings that are very common in JavaScript. You get all of these on the stack. That's kind of lovely. Yeah, I'm digging this. Yeah. A future consideration also is that even if we go really crazy on making all sorts of stack-based data variants, we still probably have about 127 discriminants left over. So half the discriminant set is unused. So what if we just make sure we're never using the top bit of our discriminant, and we create thrown value variants? In JavaScript, when you throw a value, you can throw any value. Like it's not that you need to return an error or something, or throw an error. You can throw an undefined, you can throw a null, you can throw whatever. So if we make sure that we're never using the top bit of our representation value, we can essentially turn throwing a value into just setting its top bit and then returning it. That's kind of lovely. I like that a lot. Unfortunately, this means that our code, when we're writing it in Rust, we can no longer use the question mark operator. Like if you can't just do like an enum that has the question mark operator defined on it, except with the nightly try trait. And that, I would want to use that, but we're not using nightly, so we can't do that right now. Yeah. Also, the question mark operator is quite nice because it quite exactly matches what the ECMAScript spec uses. They use a prefix question mark to say, if this failed, then immediately fail it upwards. That's the question mark operator from Rust. They also use the exclamation mark to basically say unwrap. A future consideration is also like, can we go lower? We're currently at 64 bits, but could we go to 32 bits? That would mean that our indexes would be 24 bits. That's still probably enough values to run a decent JavaScript engine. Could we go down to 16 bits? So we would have 1 byte of the variant and 1 byte of data. So up to 255 indexes. We're not using the 0 value there for reasons. That's not a lot of values in a virtual machine, because this now means that there can only be 255 objects or numbers or strings in existence in the virtual machine at the same time. And if you go over that, then it crashes. But that would be a very small virtual machine. That would be quite fun. Also, our value currently lacks lifetime. That's not really great. You can grab a value, put it on the heap, and use it hours later as if it still worked. No, the index is going to be reused probably by this time. So we need to generate actually unique lifetimes for our agents or heaps. This requires some work, but also if we get the values tagged with a lifetime and we get the heap tagged with the same lifetime, we could probably write our heap GC, garbage collection algorithm, in such a way that the borrow checker actually starts helping us do GC correctly. Because if our GC algorithm is written as, I give you a heaped, generation lifetimed item, you return me an item of the same type with a new lifetime that I give you as parameter, then you basically are forced to do that transformation of from old lifetime to new lifetime, and we're just going to essentially be assigning your given value to the place where we got the old value from. So that would be kind of nice. Okay, so what's this got to do with data-oriented design at all? And what is data-oriented design? I'm not an expert. I have, as said, I heard about this stuff last year and thought, wow, that's really interesting. Damn. It's also something apparently kind of ill-defined. People seem to have different ideas of what is data-oriented design and what is data-oriented orientation. I don't know. Lots of names. But here's my definition for this talk, at least. Know your data. Design around your data first, and only second consider objects or logical wholes. And as everything in programming, you should take this in moderation. It's probably sometimes a good idea to design around objects first and data second, but I'm not going to take it in moderation. So let's look at how data works in ECMAScript. Of course, data in ECMAScript is just the values and the heap data for that. There's prototypal inheritance in ECMAScript. There's no multiple inheritance, but the inheritance chain can change during runtime in actually two different ways. Your object can change its prototype at will, but also somebody can go change the prototypes that you are inheriting at any time. So your virtual methods can become some other methods randomly, or you can get more virtual methods suddenly. Interestingly enough, the prototype does not actually define your internal methods. The object type defines your internal methods, and internal methods are things like how do you react when you are assigned into, or what do you return when somebody reads from you. All right, so as said, an array is an object. An array buffer is an object, but it's not an array. It's completely different. Functions are objects. Everything is basically an object if it's not the primitive stuff. Array behaves like an object in every way except that it's get and set methods. So what happens when somebody assigns to you, what happens when somebody reads from you, are defined differently. And actually, now that I think about it, it's only the set method which is defined differently. Also, the spec helpfully says that whoever uses this abstract operation is an array. I don't want to be comparing function pointers to see if an object is an array. Anyway, function is exactly equal to an object, but its methods internal methods are all the same, but it has one or two extra methods, the call and construct methods. So if you look at this and you come from an object-oriented viewpoint, you're going to say, well, obviously, objects define the kind of base class, and they have virtual methods. Array inherits that object, so it overrides some of them. Function inherits object as well, and then it just adds one more or two more virtual methods, the call and construct methods. And this seems like a reasonable thing. Let's not do that. Let's instead think about how arrays are actually used. And we'll think about that first, then decide how to actually build this logical whole. So, example usage of an array in ECMAScript. They have a special property called length. It returns kind of, this is not quite true, but this is close enough. It returns the current highest index plus 1 of all index properties in the object. And if you assign an index, then the length may change. And if you assign an index that is higher than the current length, then you will create holes. So if the length grows by more than 1. If you assign length, it either drops items or creates holes if the length grows, or just might not do anything if you assign the same value. And how you normally use arrays is that you push, pop, and unshift items into the array or out of it. So those always keep the array kind of nicely compact, always changes index by at most 1. You can also sometimes create arrays with some static value, in which case it has a bunch of holes in it at that static length. And then you assign at those indexes. Sometimes you might assign length to, for instance, empty out an array. The push, pop, unshift, shift functions, those come from the prototypal inheritance. It's uncommon to put non-indexed properties into an array or to change the prototype. If you change the prototype, you're going to lose push, pop, shift, unshift, unless that prototype that you changed to also implements those. But then, like, what are you doing? Let's not look at that yet. So, and then non-indexed properties, that means properties but like foo or bar or so on and so forth. What's our time? Okay. Why would you assign those to an array? So do we actually even need the object-like properties of an array? Common usage of objects, by the way, is to assign non-indexed properties. So foo, bar, so on and so forth. It's quite rare that you would assign 0, 1, 2 to these indexes into an object, because if you're assigning to those, like, why are you using an object? Why aren't you using an array? The spec defines a special case that the index properties of objects are listed first when you ask for the keys of an object. But that's the only special case. So do we actually need the object to kind of prepare for these index properties specially? Or could they just be normal objects, and then when you ask for keys, we'll sort them for you first? So the array and object implementation in our engine is that, no, we do not need object-like properties for arrays normally. So we don't track non-index properties in an array. We actually don't track prototypes at all either. And we don't need index properties in objects. So we don't track kind of elements of an object. We don't track these indexes in an object. Objects track the prototype and their normal properties, be they indexed or non-indexed. Foo, bar, 0, 1, they're all tracked the same way. Arrays track elements, so those are 0, 1, 2, 3, 4 index properties, and then they have an option to an object. And this is basically an option non-zero 32-bit integer. So it's an optional index into the heap vector of objects. By default, an array is then only a collection of index properties. Its length is calculated. The prototype is inferred to be the array prototype, because why would you be changing it? It's always going to be the same. If you change the prototype of an object of an array, or you assign foo or bar into your array, then we create the backing object and we make this option sum. And that object can then do tracking of those things. We don't care. Like, it's gonna be slower, but why are you doing that? Don't do stupid things. As a result, our array is currently only 16 bytes in size. It might grow to 24. And then the number of items, or actually the capacity of the array. Okay, so where are these saved properties? You would normally think you would put stuff into a vector on the heap with a vector of values, and you would maybe inline some properties, but we have a heap vector or multiple heap vectors of arrays of values. So our heap contains vectors that prepare to have arrays of values of some defined size. So the array and object, when they point to their elements or properties, they actually have they know which vector of this kind are they pointing to, and then which index in there are they pointing to, and how many items in that array do they use. And property descriptors, let's just skip that. Rarely used, so we'll skip those. All right, so what is the point here? Well, it's an entity component system. Kind of, in a way, the point is to save memory, but the point is not to save memory. The point is to save cache. So all our heap allocations, whenever you allocate on the heap, it's going to be in linear memory with data of the same type created at basically the same time. Mapping through an array is just accessing values in linear memory, and this is nothing new. Every engine does this because, of course, you're going to do your array as a vector. But now in our engine, if your array contains data of the same type, that data is also probably going to be right next to each other because it's most commonly created at the same time. Like, let's say you map over an array and for each item you create an object. Those are going to be created right next to each other because they're created at the same time. And now GC marking the heap, normally or always, it's just the act of iterating through all allocated objects on the heap and following their outward pointers to whatever they depend on. Now this is just traversing linear memory. We go through the vector of all objects, and for each object we check its prototype. We make sure that we know that we should look at that later. We check its properties, and we make sure to know that we should check those later. And we go through all the objects that we have marked so far, queue up these indexes for future work, and then we repeat if we still have more work to do. We put the output indexes into queues and so on. The GC sweep just becomes a retain mut on the heap vectors. So any data that was unmarked, we drop with the retain mut, and those that we retain, we make sure to shift any heap internal indexes down by the amount of data that has kind of shifted from underneath them. So after a GC, our heap vectors are always packed with live data. GC also, let's actually kind of skip these. We also get some nice benefits to how we get new space from this. But that's yeah. So at the end of the day, our engine then has it's an entity component system where our entities are the values, the components are the heap data that we keep in the vectors, and then the systems that we have are mostly our GC, but also, of course, the user code that we run on it. But they can do whatever. But yeah, we get a nice entity component system. So this is what my friend was telling me this summer or last summer. Entity component systems. He was really, really happy with those. And I was like, yeah, that sounds interesting. Let's do that for a JavaScript heap. So, okay. What is Nova going to be tomorrow? So we're still very, very rough. It only runs a few trivial ECMAScript programs. Still can't call functions, for instance, which is somewhat important. But there's a lot of grunt work left to do for implementing more spec abstract operations. The VM implementation and the bytecode is just barely started, which is why we can only run some trivial programs. I have implemented the GC algorithm, but it's quite rough still. Although it's parallel, it's because it parallelizes like ridiculously easily. The heap needs to be made concurrent marking proof. I really want to mark in concurrent time, but this will be really hard. Having just a single mutator thread makes this more possible. I would like there to be, I'm not sure if there are, but I want to kind of find a Rust abstraction that gives me a way to turn my heap into a read-only copy of, or clonable structure, not structure, but kind of something that I can give to everyone. Like you can read from the heap, you can read from the heap, you can read from the heap, and then one object that is only allowed to, or that is allowed to read and write to the heap. So this is kind of like multi MPSC, but reverse. Yeah, the sweep is already stop the world, or is, yeah, it's always gonna be stop the world, and it's embarrassingly parallel. But I also want to make the heap concurrent marking mostly lock-free. So that means I will need to do some RCU, read copy update stuff, like if a heap vector needs to be reallocated, I need to actually keep the old allocation, copy it into a new larger allocation, change the pointer, change the length, and now I can keep going. And I need to keep the old vector memory alive until GC has finished. Then I know I can drop it. Also, I want to do feature flags, a lot of feature flags, so every feature flag possible. The 8-bit indexes, that would be lovely as a feature flag. Automatically frozen prototypes, feature flag, yes. ECMAScript optional features, feature flag. Yes, JavaScript variants. And eventually I kind of want to be the most interesting ECMAScript engine on the Rust block. I think it already is, but I mean, it's early days, very little code, very little things to show. And the only competition, I believe, is the BOA engine, which is not very interesting. They use the GC crate. Using crates, so old-fashioned. Also, it might be nice to consider being fast, And I want to do it together with you. So it's mostly just me right now. There are some other people, but they are sometimes active, sometimes not. So grab the GitHub link, take a look at my horrible code, some others as well, and come write a JavaScript engine with us. Yeah, that's my presentation.